I'm going to suggest that the speakers aim for 25 minutes or thereabouts and leave at least 5 minutes for questions. Those of you who will be up here, this is the advancer and the backer upper. There is no laser pointer. I don't think that'll be a real detriment. And with that, I think I'll introduce Chad Northington. He'll be our first speaker. Chad's with REGENESIS, and I think you'll find his presentation very interesting, as you will find the rest of these as well. Thanks, Chad.
All right. Thank you, sir, and good morning, everyone. Thank you, especially to you, the brave souls that have come out here at 8:30 on the Friday and have remained. So we appreciate that for sure. So if you had the pleasure yesterday of listening to Paul Newman's discussion on ex situ or above ground treatment of PFAS, we're going to switch gears and go below the surface today. So we're going to talk about in situ or subsurface treatment, full spectrum treatment of PFAS impacts. I know for me, one of the burning questions has been, as we've labeled this category of compounds, forever chemicals, right? The question is there a forever solution? So let's talk about that a little bit. So first of all, before we talk about the solution, let's talk about the problem. So as we're getting out there, we're starting to delineate these plumes, we're starting to see where they're actually at, and we're finding out they're pretty big, right? A lot of the attenuation or degradation mechanisms that are usually in place are not, to keep these things in check. So they're just ranging free across the remedial landscape, and in that process, they're crossing lots of sensitive receptors, bodies of water, municipal wells, potable water wells, crossing boundaries. They're all over the place, right? So we've got on-site liabilities, we have off-site liabilities. We got quite a problem on our hands, right below our feet. So what we've been doing in the in situ world, one of the approaches over the last several years is using colloidal activated carbon as a permeable reactive barrier to mitigate and slow down and retard these migrating plumes. And so that's a PRB is the acronym you might hear me use, but essentially this is an attenuation mechanism. And if you look at the ITRC definition, talk to our friends over there, they call it enhanced attenuation the result of applying an enhancement that sustainably manipulates a natural attenuation process, leading to an increased reduction in mass flux of contaminants. So we're going to dig into what that means, dig into that mass flux question a little bit, and how this helps provide a mechanism for treatment. So really in any scenario where you're using a permeable reactive barrier, there's a lot of advantages, whether it's carbon or otherwise. One, there's just no infrastructure, no O&M. It's really a passive management strategy versus an active management strategy. It's not generating waste, and in the case of carbon, we're able to treat to those low part per trillion range levels. Now there's rumors and rumblings of parts per quadrillion. Right, that's a little mind-blowing, but we'll see if the labs can keep up. But for now, we know we can get down to these PPT levels with carbon. So all of this translates to a very cost-effective approach for treatment. So what we end up seeing is that we've got a few major areas where we identify different types of impacts. So we got our high PFAS mass in the vadose zone. Often this is a very thin zone. Maybe there was AFFF, a fire that was put out, or fire training, for example. And then below that, we see the capillary fringe where this stuff's hanging out. And then, of course, the distal or further edge of these plumes where we have lower concentrations down gradient. So each one of these looks a little different. So if we look at the vadose zone, what we have is this mass that's basically due to the solid phase and air-water interfacial absorption. So they end up forming these different structures, these micelles, right? We got that hydrophobic, hydrophilic structures, these hemimicelles, these bilayers, all these things start to form in the vadose zone. When we go down a little deeper, more into the capillary fringe, it takes on a little different feel to it. So you have this same air-water interfacial absorption going on, but you have that hydrophilic head sticking down into the water and that hydrophobic tail sticking up, basically. So a little bit different look to the structure of that. And then, of course, down gradient, we have the dissolved phase mass that we're dealing with. So each one of these we want to approach, the vadose zone, the capillary fringe, the down gradient portions of these, to essentially get very rapid reduction in the leachability, the mobility, and the migration of these plumes, and try to stop them, both at the source and down gradient. And essentially, if we're able to go to the source, kind of cut off the head, as we often do, right, and then go down gradient and stop further migration with these barriers, I'd dare say, we could have a forever solution. But let's talk about that before I get ahead of myself. All right, so that's the background of what we're dealing with, where it's at, what it looks like in the subsurface. So what we have is a lot of common questions I've seen, kind of 3 categories of those, and I really want to address those today as part of this discussion. So you can see here the first one is, well, without contaminant destruction or degradation, how does this classify as remediation? How does it fit as remediation? The second is, well, how do we know about longevity? How do we know how long this is going to last? What affects the longevity and impacts that? And then finally, well, how can we really make sure we're getting a good barrier or source area treatment and getting carbon where we need to get it? So these are kind of the 3 major areas I've seen come up as we've encountered questions about this approach. So let's try to knock these out. So first of all, it's the Florida Remediation Conference, right? So what is remediation? I think sometimes we forget, but ITRC, again, our friends say it's a process used to reduce or eliminate the risk for humans in the environment that may result from exposure to harmful chemicals. Right? So reduce or eliminate risk and exposure. And we know that risk is a product of the hazard times exposure. Now, one of the mechanisms we've been using for a long time to deal with this is attenuation, natural attenuation. And EPA defines that in 3 different ways. One is transformation of the contaminants to a less toxic form. So that might be like enhanced reductive dechlorination, ERD, where we take PCE, reduce it to ethene, innocuous ethene, right? That's not what we're talking about here. Reduction in contaminant concentration. Maybe we use chemical oxidation. We destroyed these compounds. Also not what we're talking about here. But the third one is reduction in contaminant mobility and bioavailability. So we're talking about that one. So reduction in contaminant mobility. And basically by binding up the PFAS in this matrix of carbon, we're able to eliminate the exposure and therefore we eliminate risk. Right? We've been doing this for quite some time for other compounds. We've been doing it for recalcitrant type organics. We do it for metals where we're not actually destroying them, but transforming them, right? So similar concept. And I've put a picture up here of Dr. Chuck Newell. You may have heard his name before, Charles Newell. He published a paper not too long ago with some of his colleagues, and he's one of these guys that when he speaks in our industry, you listen. He's published and co-published a lot of articles and papers, software that you may have used before. So he had recently said that the potential enhanced attenuation technologies for PFAS plumes implemented in the saturated zone includes adding sorbents to increase retention. So there's different types of sorbents. Activated carbon, colloidal activated carbon is one example of those. So this is a path that is being promoted and by folks that are in our industry that have been in it for a long time. So it's nothing new, but it's new because we're talking about PFAS and how we treat it. So just to make sure we're on the same page about when I say colloidal activated carbon, what am I talking about? There are a couple different forms, a couple different technologies, but essentially it's 1 to 2 micron scale carbon. So to put that in perspective, that's about the size of a red blood cell, right? The size of bacteria, we're pretty small. So it's not powdered activated carbon or granular activated carbon. This is really small stuff in a suspended colloidal liquid form. And what that allows us to do is get high volume, wide area distribution and inject at low pressures. And so we can get this stuff spread out in a way that we basically convert the subsurface into a carbon filter, kind of like a Brita filter in the subsurface. So, I always go back to these pictures. I've never gotten tired of them. It's been 7 years this week, actually, that I've been using these photos. But the pre- and post-injection scanning electron microscope images tell the picture. Essentially, we are painting, I like to say, the surface of the aquifer matrix with this carbon. That becomes a permanent part of the aquifer matrix. So, again, conversion to a carbon filter without changing the advective transport or the hydraulics of that zone. It's not blocking up the pore throat diameters, still wide open for contaminant transport and then sorption. And if you look at a macro scale, you can see here, carbon's a great tracer in and of itself. So when we tackle what we call the mass flux zone, kind of where the bulk of that contaminant mass is migrating, you can see the distribution of that carbon in those cores. And even in the case where maybe you have a less permeable, maybe a confining unit below like a clay, if anything back diffuses out of that, the carbon's still there acting to manage that long term. So I wouldn't say colloidal carbon's a new technology by any means. It's been a decade plus in maturity, but the use of it in the PFAS world has been going on for about the last 6 years for treatment. And I've seen, I think, over 26 sites now globally that we've treated with this approach. And there's a lot of folks out there, third-party research that's going on with academia. You guys might have heard Dr. Paul Hatzinger with APTIM. I know there's a lot of APTIM folks here today. He's one also doing some third-party research, EPA-funded work. So a lot of folks exploring these concepts and the use of this outside of REGENESIS. So that was all about how does this fit remediation, right? The use of carbon for treatment. So now let's shift gears to, well, how do we know how long we can treat? What about treatment longevity? So first of all, we have to go back to what we call the isotherm, or more specifically, the Freundlich isotherm. And what this is the equilibrium concentration, the dissolve phase to the sorb phase for a particular mass of carbon at a particular temperature, isotherm. And what's unique about this is often technologies are more efficient at the higher mass concentrations, right? That's where they do the most damage. With carbon, you can see this curve dropping down, and it's got a high efficiency because of that at treating to low levels. So this is essentially why we can treat to that PPT range. And you can see a couple candidates here, PFO and PFOS, the two celebrities in the PFAS world, and comparing that to PCE. And I don't think anybody would argue that PCE is not a good candidate for carbon sorption. So you can see that compared to the same reduction for those three compounds, we need about 2 to 3 times less carbon to achieve the same results with PFO and PFOS as we would with PCE. So those guys love to be sorbed. And then in terms of modeling, Dr. Jeremy Bernstein out of Bath, England, has developed a software called Plume Force. I always have to say it that way. It sounds kind of, you like that? That's like Plume Force, like everybody's paying attention now. So what this is basically is a fate and transport model, long-term predictive model for figuring out, can we really tell in space and time what's going on at a particular point? So you may have heard this before. All models are wrong, but some are useful. So what we've been doing is doing a lot of sensitivity analysis, comparing results to what we had predicted to make sure this model is in check, and it has been. And what we're looking at a lot of different factors, competitive sorption amongst the compounds. We're looking at compound-specific isotherms that we just talked about. So each compound has its own isotherm. And not just its own isotherm with carbon, but the type of carbon. So colloidal activated carbon has a better isotherm than, say, granular activated carbon. Okay, so that's something to tuck away in the back of your mind. And then we can look at degradation. So a lot of these plumes are commingled. They might maybe with BTEX or chlorinated solvents. We can still degrade those compounds when they're sorbed to the carbon and open up new sorption sites to prolong the longevity of the carbon. And we do that for a lot of different classes of compounds. So there's a lot of parameters we throw into this. Some of those are fixed, right, based on the geology, the hydrogeology, but then we can start manipulating some things. The dimensions, we can manipulate the dosing and see what the impact of the longevity is on the barrier. Again, there's been a lot of third-party type work done. Dr. Grant Carey with Pore Water Solutions out of Canada, he was one of the first to model colloidal activated carbon longevity. And this was a commingled BTEX site with PFAS up in Canada. So that's a great article. If you want to dig into mass flux and longevity and some third-party modeling, or if you don't sleep well at night, I recommend all these articles. They're great. So check into that. But again, third-party corroboration. So part of what the longevity boils down to is retardation factors. So I'm gonna dig into this a little bit. So first of all, what putting carbon into the ground allows us to do is engineer the retardation factor, okay? And we actually, part of that is we're changing the distribution coefficient, which is that KD value, that's the ratio of the sorb to dissolved phase mass. So we can change that by orders of magnitude by injecting carbon into the subsurface. And that KD value is part of the calculation for the retardation factor. So when I say retardation factor, if that's an unfamiliar term or maybe you haven't heard it for a while, let me remind you it's the contaminant velocity relative to groundwater, right? So an R value of 1, they're moving at the same speed, basically, the molecules. R value of 2, the contaminant is moving at half the velocity as groundwater, et cetera. So typically what we see are R values of maybe 1 to 3 for VOC situations, typical. But when we start putting carbon in the ground, for example, at a standard dosing at about 100 ppb TCE plume, we change that value to 600. A couple orders of magnitude difference. Now think of that as like a slowing down of the molecule moving through the barrier, right? So we've slowed it down by a factor of 600. If we think about PFOA at like 100 ppt concentration, which would be typical in the distal edge of a plume, that value goes up to over 12,000. So what's that mean? It means this table. It means for these compounds going from low molecular weight to high molecular weight, there's a red line there that says, hey, these guys are regulated somewhere by some states currently. You can see that for PFBS, at a standard dosing, at a common concentration, we're talking about a century of essentially immobilization in that barrier. And that only gets better with increasing molecular weight, up to over 1,000 years at a standard dosing. And we can change the dosing and get it even better. But just to give you a picture, when I say longevity, we're not talking about a year or two. We're talking about tens of years, hundreds of years of immobilization and retardation of the plumes with one application. So that's the longevity question. And I got one more here I wanted to get into. So how do we know we're getting carbon where we need it? How do we know it's being put in the ground as designed? So this is a bunch of field techniques that these really apply to any sort of in situ work. So what I'm going to say here doesn't just apply to colloidal activated carbon. So the first thing is a pre-application step. So something that we do prior to going full scale. There's a mobilization ahead of time. We call it design verification testing, DVT. So, when you do site assessment, you're delineating the plume, you're kind of figuring out risk, but that information doesn't necessarily give us what we need for remedial design, right? So there's a whole nother step where we might want to dig in for the parameters that we might not get from the site assessment that we need for remedial design in situ. So that might be more detailed stratigraphy, high resolution characterization data, flux measurements. I'm going to talk about that a little bit. And then maybe looking at the volumetric acceptance rate of the aquifer. How much volume can we get in there? What are the pressures and the ROIs we might expect? And all of this information we then take back to the original design and massage it, calibrate it, and optimize it before we even get to the full scale. So it's an important step. And I'll tell you why here. So where we've looked at these sites and identified what we like to call technical blind spots, kind of data gaps, about 80% of the sites generally have something like that in some major category or multiple categories. And the importance of that is if we miss one of those, we risk non-performance or underperformance. And about 60% of the time, about 2/3 of the time, we're going back to the design and changing some things. And often it's a cost-neutral change because we're maybe changing the dosing or moving some stuff around or changing the treatment interval based on what we learn during design verification testing. So there's an avoidance cost here by not having underperformance or non-performance at a site. So a really important step. This slide is meant to overwhelm you, especially Friday at 8:30 a.m.
Succeed.
Good, I just succeeded, thank you. But what I do want you to focus on, the point of this is there's a lot of different techniques depending on what your data gaps are, right? And depending on what your budget is and what kind of resolution you need. There's all these different things in the smorgasbord of DVT that you can choose, but the 4 boxes represent the important categories. So soil physical properties, transport zones and contaminant flux, injection rates and distribution testing, and then the soil and groundwater geochemistry. So those are the boxes we want to be checking for in situ design, carbon or otherwise. So one of the things I do want to focus on is this device called a passive flux meter, PFM. In this case, we use flux tracer. And what this is, we talked about mass flux and how that's important for enhanced attenuation and figuring this stuff out. Basically, what this allows us to do is vertically delineate the Darcy velocity as well as the contaminant distribution in the zone where we want to treat. And this, often we have like a site geology and someone says, well, the conductivity is this because this is the site soil, right? That's a pretty broad assumption. Or maybe you've done pump testing, aquifer pump testing, slug testing, and you got some values for conductivities. That's good too, but it's really more aligned with pump and treat approaches where you have recovery wells and such. When we do sorption, we want to use sorption-based test. So this is a carbon-based type of device. And what we get to do is get real surgical, real strategic with our design by taking this information on this high resolution on generally 1 to 2 feet intervals. And basically these things are deployed for 2 to 3 weeks in an existing monitoring well, pulled out. There's alcohols that wash out, and based on the time and what's left, you can back calculate the Darcy velocity and then take samples for the distribution of the contaminants on that carbon core. And then we can go and look at mass flux across that zone. And you get outputs that look like this and mass flux calculations that tell you where you need to put how much stuff. All right, so this is a really important tool in the realm of permeable reactive barriers with carbon. So that's all the stuff we might do before we even get out for full scale, right? That's getting it right before we get to the big event. So we have another step called placement validation. So this is essentially happening in the field, on the fly. I call it dynamic remediation. You may have heard that term, where basically we're looking at things while it's happening to verify what's in the design matches what's happening in the field. So we can do a lot of different things. Often we'll take soil cores. Carbon's the great tracer, so we can look at cores to see it's distributed. And then we can look at colorimetric test kits, where if we have influence in the well, which we want to see, that means we're getting good radius of influence, we can take that colorimetric test kit and say, well, here's the dosing that we're getting. Does it match what we designed for? And we can make adjustments, and we can put in piezometers and see if we're getting the radius of influence and distribution that we anticipated in the design. And if we are or we aren't, we can make adjustments right there, call up the design team, talk to the field team, and make things what they're supposed to be based on the design. So it doesn't stop once it's on paper in the design. So we had 3 big questions today. How does PFAS and colloidal carbon fit the definition of remediation? I think we got that one covered. The second one is, how long does this stuff last? How do we know? How do we model it? We got that one covered. And then finally, can we effectively apply and implement a carbon barrier in the subsurface to truly convert it to a carbon filter? So check. I think we got all 3. So those are 3 questions I hear a lot, so I'm here to listen to any questions you guys might have. We have a little bit of time left, it looks like. It's a little early. I've had a little bit of coffee, so I think I can handle 1 or 2 questions maybe. So, but thank you.
If there are a couple of questions for Chad or comments.
Yes, ma'am.
I'm sorry, yeah, go ahead.
Uh-huh. Yeah, so she's asking about the table that showed the retardation factors, and we talked about longevity, number of years and such, and the kind of that ranking. So yes, the difference that affects that are twofold. One is the carbon chain length, right? The longer carbon chain lengths, the higher molecular weight, the heavier stuff. As with any carbon or any compound class, is going to stay sorbed better, right? And then also the functional groups, like you mentioned, the carboxylic acids or the sulfonates. There's a difference that affects how well they're sorbed. So that even if you have the same number of carbon chains, there's still a relative difference based on the functional groups that are attached to them. Does that make sense? So the shorter ones are going to be retained less time. Yeah. Mm-hmm. I see what you're saying. Yeah, we'd have to look at the isotherm specific to the carbon to understand that, but I'm not sure why they're flip-flopped. That's a good observation. Yeah.
Are there any other questions or comments? I have one, and I will say, oh, I'm sorry, go ahead, sir.
So I have a short question. There was the software that you introduced, the plume force, that you just work with certain compounds, like certain PFAS. How is that?
So it's meant for lots of different contaminant classes, just not PFAS either. There aren't isotherms for every single PFAS compound that we've discovered yet, right? So there's a process, and we can make assumptions and conservative assumptions if we need to. Like I said earlier, the colloidal activated carbon provides a better sorption capacity than, say, granular activated carbon. So if you're using the granular activated carbon or a powdered activated carbon isotherm, it's actually going to not represent what we can truly achieve with colloidal. But we can do that for all of those compounds or make assumptions based on existing data or the shape or nature of the compound itself to figure that out. Does that make sense?
Yeah,
Right. Right. That's right. So I think like most folks, we're starting with the priorities, the things that are going to get an MCL quickly, like PFO and PFOS, or the ones where the states are regulating them first. And then I think a lot of that will continue to follow behind in terms of dialing it in even more. So, but they do put a demand on the carbon. We can't ignore the fact that there's other stuff in the mix, and we have to include that in the design. Not just the contaminants, but even the non-target compounds that put a demand on the carbon that are naturally existing organic matter and such. And that's the same if you're doing a petroleum site where you have BTEX and some other compounds, but what about your total petroleum hydrocarbons? They're putting a bigger demand on the carbon. So you have to take all of that into account, and we do in the modeling. Mm-hmm.
Any other questions or comments for Chad? Okay.
Thanks
Thanks
guys.
very much, Chad.
Appreciate it.